first sort of big segment of our work at the Human Media Lab at Queen's was on attention sensors and being able to sense when a person is looking at another person or at an object, and then being able to direct attention, but also how to avoid interrupting in inappropriate moments, and basically taking a conversational metaphor. Well, even there, the whole premise of putting cameras everywhere, and I had an argument with someone at a conference once where he was basically making an interface that required the camera to be turned for privacy reasons, and sort of like turn off the camera. So not just turn off the camera, but communicate the camera's turned off. And I said, that's ridiculous. I mean, the camera's just a sensor. It's not used for imaging, and we throw away all the other data. But now what we're seeing is an incredible amount of nefarious use. People are actively taping off their webcams on their laptops because they're worried somebody might be peering through them. And guess what? People do. The world has changed dramatically from the world I grew up in, which was a world in which only researchers had access to the internet. Everybody was well behaved. There was no such thing as spam. And there was no such thing as hacking. Hacking was a very positive term. Hacking is what Tim does when he takes some Lego bricks or this sensor and puts it together in a different configuration. So we have to stop. We have to pause and say, like, even with the things that we develop for good, like Facebook, social networks, there are huge problems. I was attending a talk organized by Zia Tong of Daily Planet a couple months ago. There's a group in Toronto that looks at surveillance of Facebook networks by governments, and actually people get arrested because of government hacking into their Facebook networks, finding out that what their patterns are. And we were just sort of commenting jokingly that if Mark Zuckerberg ever decides to run for president, he's probably going to run against Kanye. He would have knowledge of the electorate at a scale that's like unprecedented, right? He's more powerful than the CIA. So coming back to Earth and coming back to virtual reality, we really need to start thinking about some of the social implications of living in a virtual world. And Mark Bolas argued at Microsoft Faculty Summit in 2013 that we already do. And this is exactly what's going on. People are glued to their screen. They're living in a virtual world, yet they are operating in a physical world. And so I think that much of our research has been dedicated over the years to bringing people back to the physical world by embedding information in the physical world. And that's what this talk is going to be about. I'm very concerned about what's happening with virtual reality and how this might translate to an even worse scenario. Don't know if you saw the Mark Zuckerberg photo where Mark was walking down the stairs in an amphitheater with developers and journalists all wearing Oculus Rifts. And what was really interesting about it was that the most powerful person in the room was not wearing one. He was the one walking down the stairs, and everybody else was oblivious to that. And so there's a real power to actually objecting to screens, to objecting to being enveloped by information at all times at the exclusion of the real world. So what if we flip it? So this talk is about using a new form of 3D graphics display called the light field. Well, it's not so new, but it's about 100 years old. The first patent was 1903 or something like that, but it's only now becoming practical towards getting what I call real reality interfaces, where the interface is completely embedded. So virtual reality is all the hype. This is actually a pretty old picture because it was all the hype before. There was a hype cycle in the 80s when Jaron Lanier was doing his thing with virtual reality labs. And this is Scott Fisher at NASA sort of promoting the use of a data glove. Where did the data glove go, by the way? But this sort of image of people being able to immerse themselves in a new world, but with very heavy tech requirements and basically blocking off their perception, to me, is something that is very, very scary. And I'll give you an example. This is something that was a kind of a follow-up to our work on telehuman by my good friend Shahram Azadi at Microsoft. And he, let's see what happens here. There we go.
Now the camera that's filming me has a HoloLens tracking system attached. And this allows us to take these 3D models and composite them in real time into the real world, as you can see here. And that gives you a sense of the fidelity of the reconstructions that we can achieve. Once we have these reconstructions, we can texture them. We can then compress the data and transmit the data over to the other side. Over on the other side, a user wearing a HoloLens.
And there's the problem.
Remote participants live.
So this is very cool research, but now he's wearing this thing that closes him off from the environment. Now you can argue, okay, these things are going to be lightweight. They're going to be basically like glasses. And yes, for augmented reality devices, that may be true, but virtual reality always closes off the environment because otherwise you can't create a new environment. So this is a real problem, particularly when you're talking about multi-party conversations, for example. So there are actually two approaches to augmented reality. We're currently doing the first, which is to alter human perception. And this can take the form of taking over the eyes and projecting stereoscopic images into the eyes. It could also take the form of potentially hacking the eyes and going straight into the retina or doing laser projection into the retina. It could potentially take the form of taking over V1, which is the vision center in the brain, and stimulating that so that you wouldn't even need to wear glasses and you would be able to somehow project images into or overlaying them onto the environment without wearing anything. But it would still be a form of human augmentation, which I think is a euphemism here, human modification in order to be able to create this digital experience. Now, how about if we do the other thing, which is to alter reality? If we can alter reality in a way that makes you experience something within the context of reality, wouldn't that be much more powerful? So there's three distinct stages of a push towards that we've been sort of finding as we went along this path of research. This wasn't necessarily something that was planned out, but if I look back at what we did in the last 17 years that I've been at Queen's, it's very clear that this path is being taken. The first is projected reality. So what we do here, this is augmented reality projected on real objects, usually 2D, but on 3D objects. And this has been going on for about, 15 years now. It started off at Merle with shader lamps. So this idea is that you get a projector, and instead of watching a display, you project on an object. And here we see a version of it that's projected onto three-dimensional objects. This was done in 2001 dynamic shader lamps. So what they're doing here is basically, this is projection mapping. This is really taken off in the arts by projection mapping on buildings. But here we see actually objects that it can move around and maintain their texture mapping. So we're mapping the textures directly onto a three-dimensional model of the object, which is then projected back onto the object and kept in sync with its movements. So it turns out we did quite a bit of work on that ourselves, inspired by Digital Desk by Pierre Wellner. Digital Desk was a first attempt at bringing the graphical user interface back into a real desktop metaphor. So what we're seeing here is paper being used as an input device using a pen. You can enter numbers by circling them into a virtual calculator projected on your desk. But this was all still very much 2D, and you couldn't really move stuff around too much. So in 2004, we developed this thing called paper windows, which was a form of active projection mapping where we didn't just project onto a shape by modeling the shape, but we actually actively followed the shape using a Vicon motion tracker and using markers on the paper. When a user would fold the paper, the shape of the projection would change. There was huge lags and there was all sorts of problems, but recently at the University of Tokyo, they showed a system that can do this at 4,000 hertz, and you can actually sort of like wave the paper around and the projection stays put. So this is a form of augmented reality. Now, we did this because we wanted to move towards flexible displays where the actual paper is a display, and we didn't have them, and that's why we use this as sort of a prototyping tool. But it's interesting to look at this from the point of view of projected augmented reality. Next, we did a whole sleuth of work.
We use paper notes to control and interact with numerous devices.
I don't have control over the volume, but what you see here is this idea of what if you had a sticky, and it could be a context menu on a computer or an object. You could literally stick this on anything and then control it using a home control automation thing.
we augmented a standard paper note with small infrared dots to enable real-time positional tracking. And with custom software and hardware, we developed a prototype environment within which we could use our Stick Anywhere context menu. Sticking the note on a computer, for example, could bring up simple on and off options. The note can be placed on an object, such as a lamp, used to turn the lamp.
Anyways, you get the idea. We then made a whole workbench, which actually was intended to sort of introduce the cell phone that had a wraparound display. So three-dimensional objects that were projected on from all sides, but we kind of sold it as a workbench for design. And the first iPod was in fact a styrofoam thing with graphics on it, just as a mock-up.
Now I can take the sticky and put it on my prototype, and then I've got a screen. Now the problem, of course, is that I have no way of interacting with this screen. So how can we make these hardware prototypes behave more like real computers? That's what display objects is all about. Here I select an iPod-like device, and you see I can move it anywhere I like, just like a real device. Now it needs a dot, so maybe I put a dot on there, and I can move that around as well. Now if I hit this button, I can make this a fully functional icon.
So then we moved on to more curved objects. This is a projected on Cocan. The reason we chose a Cocan was because it was the most unlike a computer most unlike a computer or technology device that we could think of. And that turned into this. Here we see the sort of active version of it. We could run commercials on it. We could do like games and draw like prizes or something like that. And we're actually seeing some of this in the stores now on real Coke bottles where you can use QR codes to do the same thing. But it turned into this vessel, which was a startup came out of our lab. Unfortunately, it didn't succeed, but it did get into the Apple Store. For some reason, my videos aren't playing. There we go. So Vessel was supposed to have a screen on it, but it was too expensive to do so. So it became this self-tracking beverage container that was part of sort of the Internet of Things. And you could pour a drink in it and it would detect what the drink was and then store the calories that you consumed as you consumed the drink, because it would also track how much of the drink you would consume. And when we prototyped this in the lab, we had versions going that could detect the difference between Coca-Cola and Pepsi, but even Diet Pepsi and Pepsi. So moving on to bigger and bigger objects and sort of exhibit style objects, we started working on spherical displays. So as you see, the shapes are getting more complicated and the applications are becoming more refined. So this was the world's first interactive multi-touch spherical device. It came out roughly July 2008. And this was the subsequent project where we took augmented reality really to the extreme using stereo glasses. You could walk around this device and it would track your head position and you would be able to see this, in this case, this moon lander from all sides. And this was called Snow Globe, was presented at CHI 2011. So this is clearly a form of augmented reality on the object, but we're still wearing stereo glasses in order to perceive this. Now, what to do with cylindrical shapes? Well, cylindrical shapes fit the human body, and so the idea emerged of creating a sort of pseudo-holographic telepresence systems called Telehuman, and it worked exactly the same way, but we were using, just like Sharon was explaining with the Microsoft Holo Transportation, we were using a Kinect system of 3 Kinects or more to create a 3D active model of the user, then teleport that to the cylinder, and then users could walk around this, but with live video. And it gave a really, really nice effect. And it was spoofed by the hit show Silicon Valley a couple of years later. So there's bad language in this segment, just a warning.
Yes. We're going to call him up on the Telehuman. It's amazing. It's holographic 3D teleconferencing technology that we've acquired. It's going to feel as if Gavin is right here in the room with you. Oh, it's him! It's him!
Hello, Nelson. Thanks for meeting with me.
Whoa! Hi, that's cool. Am I a hologram over there too?
What? No, of course not. Question. Do you still talk to Richard Hendricks?
Yeah. I mean, not about Nucleus or anything.
Why would he enter Pied Piper and TechCrunch Disrupt? I know a lot of big players have come out, CM or what have you, but Peter Gregory's already funding him. Why would he let Richard do this? It makes no sense.
I don't know. I didn't even know Richard got in.
Is Peter Gregory toying with me? Is he trying to make Richard seem folksy? Like some aw shucks boy genius entry in everyman's competition?
Mr. Belson?
Can you hear me?
Hello?
Can you hear me?
Yeah, it's sort of fading.
Hello?
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 I'm hearing you. It's just the image is...
Nelson, shut up for a second. If you can hear me,
Make a gesture.
Is it... I hear you. Is this...
I have no idea what you're saying, Nelson. Nelson. Can you help me, please?
Okay, I think what happened was when you set it up, you forgot.
I didn't set it up. I paid one of you people to set it up. Just fix it.
Okay. Here's the thing. It's not working. The audio's still working. You could just use that.
The audio is working? Excuse me? I paid $20 million fucking dollars to acquire this company. Fuck you, the audio.
It's not unlike our real experience as a telehuman. But so step number 2, why don't we move to holographic reality? Now the telehuman wasn't it, because it still had to track where you were and you still needed to wear stereo glasses. But there is a new technology, and as I say, new is a relative term. The patents are from 1903, where we can actually not just image a pixel, but image a light ray. And what does that mean? Well, it means that you have an angular pixel. Because in the real world, how many of you have ever swam underwater without wearing goggles? Right, that's actually what the real world actually looks like if you don't have a lens focusing the rays onto your retina. So every object, every part of the world projects light in every direction, and that's why it's blurry, because multiple rays will hit your pupil of the same point. And by using lenses such as your cornea, which is your main lens in your eye, and the crystalline lens inside your eye, you focus that light onto a single point again. Now, if you develop a display that actually has that blurriness feature, or better to put it, has each pixel rendered for each angle, you can actually create a holographic display. And that's in fact what a hologram is, except with holograms, this is done using laser light, creating diffraction interference patterns that then recreate the delays in the waveform as it hits an object and wraps around it. So there's 3 main ways of doing this using our current technology. One is using parallax barriers, which block different pixels. So you represent each angle, and then you put a hole over it, which is essentially a pinhole camera. And that then blocks your view of other pixels. So depending on the angle, you'll see one of the pixels underlying it. And then there's projector arrays, where you actually represent each image from each angle and project each one using massive amounts of projectors and then retroreflecting it into the eyes. And then there's microlens arrays, which drop a fisheye lens right on top of a pixel array. And then the pixel array gets spread into different directions by the lens. And each of them has their own properties. This is how a parallax barrier works. So you got a left eye, you got a right eye. The left eye here traces back to that pixel. The right eye here sees that pixel. And then if you shift them, you get motion parallax. Right? Motion parallax is just multiple perspectives, but shifted through space. Retroreflective projection, we see this here with the invisibility cloak being used for the ice bucket challenge. Interesting to note that once he throws water on it, it stops working because it requires an air barrier in order to get the retroreflector to work. Retroreflectors tend to be either glass beads or little metal cages that are like cubes that basically reflect the light back to wherever it came from. So now it stops working. So here we see how that works. So there's this is what happens normally in a smooth surface. You get these reflected light basically going in every direction. with a rough surface. With a smooth surface, you get specular highlights, which you can see all over the room here. And then with a beaded surface, a retroreflective surface, it actually reflects the light right back. So a mirror does this, but a retroreflector does that. And if you have an array of projectors, like here, you can do a similar thing with the parallax barrier. You're basically projecting an image. It's reflected right back into your eye. So your left eye will pick up the image from this projector. Your right eye will pick up the image from that projector. And then as you have more projectors, you get motion parallax. So Telehuman 2, which we're currently working on, this hasn't been published yet. But we built a projector array around a retroreflective cylinder, and that cylinder is only retroreflective in one dimension. So it's diffusing the light in the vertical, but retroreflecting it in the horizontal, because people tend not to do this. And what that means is we don't have to have a ball of projectors around it. All we need is a ring. What it also means is we can have the ring above the eyes rather than exactly where the eyes are, so you don't have a projector blocking your vision. And here's the effect. So it's a lot of projectors. And each of them is a computational device. Each of them computes and renders the angle from that position. And when you stand there, you see the entire 720p image from that position. And then we use 3M retroreflective surface in order to bounce it back. This is our setup for capturing people. This is now using visible light cameras because they have better properties than the Kinects, but we still make three-dimensional models out of them. And here you see how they project. We see a little bit of ghosting. It's also very hard to capture using a regular camera, but CMOS camera. But you can actually, the effect is you can walk up to this thing and you basically see the person appear in space without wearing glasses and without head tracking or anything. And you can actually have a multi-party conversation using this device, where people are co-present, see each other, and when I stand over here, I see the side of your head, and when you stand over there, you see that side of the head, and therefore all the cues, spatial proximity, body orientation, eye contact, are accurate. So the third technique is microlens arrays. And here we place a lens over a pixel block, and what that does is it picks up the pixel block, and very similar to the pinhole actually, flips the image in both directions and projects it into the world. And so what we actually put on the display is a flipped image. And that flipped image is an image of what the image would look like if we had a camera in that location looking at the three-dimensional object. So imagine that what you render on the display is a camera array that basically envelopes the entire object. So you have, let's say if you have 160 cameras by 104 cameras, you get 16,640 different images. These are then each rendered onto 80 pixels on a phone display. And then you place a lens over each of these 80 pixels, and they project it back just as if there was a camera there projecting it back. Here you see the effect. This is what the image is that we're going to see. It's actually a three-dimensional sort of pyramidical structure. But this is what we project on, which is these different viewports and then flipped both ways. Now, this is our microlens array. We had this manufactured in Holland. These are very, very tiny structures that are placed on basically 3D printed droplets. The control over the shape of the lens is not great, so we're looking into better techniques. But there's a whole industry on creating holographic lenses and tiny structures. CDs are made in the same way. So that's a bit of a work in progress. We developed a smartphone called HoloFlex, which, because we did a lot of work on flexible smartphones, which I'm not talking about here because this is kind of what we do next. But because we worked on flexible smartphones, might as well make it flexible. So what we see here is a flexible microlens array, and then a multi-touch sensor deposited on a faux LED, and then a flexible array of batteries and circuit boards on the side. And that's what HoloFlex is. Now, because we made it flexible, there was this interesting property where you could bend the phone. And we've done a lot of work on flexible devices. And one of the things we've learned from all these prototypes and tests is that bending is very good for Z input. And this is literally what we're doing here. So as you bend the device, you see here we're trying to do a target matching task of two of those pyramidal triangles, structural trying to project them over top each other in 3D, and we can use the multi-touch and the Z by bending, and it's a beautiful way of interacting with your phone in the third dimension. So here's some stuff we did with this. Here we see 160 by 104 pixel display doing Angry Birds, where the Angry Bird is being launched by actually physically bending the device and then letting it go, and then it literally jumps out of the display. Now, I can't show you this because this TV is unfortunately not yet holographic, but someday it will be, and it's a really, really cool experience. Holographic teleconferencing, where we actually can look around the Skype video, and we can do that to the extreme, because when you bend the screen, we can actually redistribute the pixels. You see that happening right here. There we go. The model changes slightly, and now I can actually physically look around it. Even the screen is bent now, and I can, I can't quite see the nose sticking out, but almost. And this is a very practical application where we're using the Z-bend in order to position a handle on the famous teapot model, and we're positioning it in the Z by pressing through in the display and then letting go. And when you let go, it stops. And now you can 3D print the thing. So this screen will render to anyone, any point of view. It's multi-user by default, and no glasses needed or anything. Okay, well, step number 3, real reality. So the ultimate display would be a display in which we have control over matter. This is Ivan Sutherland in 1965. Ivan Sutherland created the first virtual reality display around that time. It was called the Sword of Damocles. And he said handcuffs displayed in a room, there's the handcuff again, would be confining, and a bullet displayed in such a room would be fatal. This is not our goal, but these are his words, not mine. So what is a real reality interface? Well, it's a user interface that cannot be distinguished from reality. And perhaps holograms are only the first step. They must be indistinguishable in terms of stereoscopy, having end perspectives, sound fields, so you can walk around it and the sound is located, force, self-actuation, weight parameters that can be discerned as if they were real objects. Even if you pick up like a bottle and bring it to your mouth to drink, you can do all that with eyes free. You can close your eyes and still do it. Why? Because there's so many parameters of weight distribution that you can sense using your kinesthetic muscle receptors, and that's all lost in today's interfaces. And of course, tactile, heat, and skin pressure parameters. So without any form of human augmentation. So the opposite direction is to have people walking in a treadmill, which is a hamster ball, with their heads augmented and an exoskeleton on, and that's not a future I want to live in. This relates to programmable matter, which was coined by Toffoli and Margulis in 1991. So think of an interactive form of programmable matter where small parallel cellular automata nodes capable of geometrically shaping themselves in 3D space could create any kind of material structure. If we could do that, we can physically represent data. But there are some challenges. So this is the vision. And this was a video that was done in, in I believe 2007 or so by Carnegie Mellon. And it was envisioned as an advertisement from 2013, and I thought it was a little bit optimistic.
A powerful new medium.
So here we see these like little robots that create a display that's actually tangible. You can pick it up, you can mold it. Has anyone seen Big Hero 6 with the crazy flying thing? That's what I'm talking about. All right, so that didn't happen in 2013, but a lot of researchers are working on it. We call these little things CADMs, this is an enduring goal to try to make a massively parallel system that can then act as sort of like physical voxels. Here we see some work by MIT where they're using a 2D system in order to create sort of physical experience where each pixel has a physical representation. The problem with this kind of display, while very cool, is that you cannot do overhangs, you cannot do holes inside the table, and of course it always is, always has structural integrity because every pixel is lifting up its own weight using an actuator. So this is a relatively easy way to do it. We see two-dimensional systems. This is a kilobot system at Harvard, which was done a couple years ago. This one is actually interesting because it is self-organizing. So I'm not sure what it's trying to do here, but it's trying to make a shape, and each robot sort of knows where to go based on some simple parameters of shape that it's trying to adjust and stay with its neighbors. Recently, Stanford, Sean Fulmer, who did the Inform table at MIT, created these bots, zooids that are tiny bots that can rove around really quickly and create sort of graphical structures that are tangible by moving them around on a surface. But here again, structural integrity is not an issue because these things are two-dimensional and on the surface. So we want to move beyond that. So there's been some work at CSAIL with little gyros and sort of Lego blocks that can jump around. It's really hard to move blocks. And as you can see, they can I don't know how many takes that took, but you know, I don't want to depend my life on a propulsion mechanism like that. So some of the technical requirements for these real reality interfaces is that they are 3D and physical, that they are modular, that they are self-actuated, massively parallel, that they self-assemble, they're self-powered, and they're nanoscale. And the final one is not obvious that they're self-levitating. Why self-levitation? Well, I'll show you. If you want structural integrity at any moment, particularly during animations, you need to cancel out gravity, because if you have an overhanging structure of these nanobots and you move the overhanging structure like I'm doing right now, the bots are just going to fall down. So we believe that the only way to actually do this right now is to take drones. And so this is called the BitDrone System. We developed it 2 years ago. And what we see here is different versions of drones. We ended up settling for the Shape drone, which is a nice sort of Lego-style brick that's a self-levitating Lego brick. And you can just put it somewhere and it stays. It has all those properties of tangibility. It's extremely low resolution. But what you see here is a user interacting with some BitDrones to do a cone tree menu. So there's some friction that is simulated in the drone. So as he spins the menu, it kind of comes to a stop. He selects a file. The drones open up into a 3D window. So these are the anchors of the 3D window. And he places a shape drone in there in order to create the first voxel of his three-dimensional model. There's another one flying into the picture, takes it, puts it somewhere. So this is sort of a physical handling of this programmable matter. But of course, you can also sort of 3D print things on the fly with this if you had enough resolution. One of the big problems with these drones is that they don't like flying over the top of each other. So we're still kind of in a 2.5D domain. We now have 16 drones, and they can actually fly in a carpet, and we can do up and down animations on this carpet, which are really, really cool. But this was the first version, which we presented last year. Here we see a display drone, which actually has a full-on 1080p display flying around, and we can present a menu on that that's not just context-aware, but proxemic. So I can just sort of do this, and boom, there's my menu. And this kind of harks back to the stickies I was showing you earlier. And I can change the color of the drones by selecting them. Of course, I can do multi-touch gestures, such as enlarging and shrinking the model. And the third drone is just following suit. I can also rotate the model. And then, because of the sparsity of the initial system, now note that Ivan Sutherland's original sort of Damocles virtual reality system only had one cube that he could look around. So we're making progress. Here we're seeing the display drone used as a telepresence system where you can just rove around the room. We created an architectural model that was very sparse. It was based on an architectural model I found online, and this is what the result is, and this can then be translated to a file and printed or whatever. So limitations, many, many limitations. As I said, they can't fly over top of each other, but also here we see a voxel-based rendition of a Volkswagen Beetle. Look how many voxels you need. Now, we don't necessarily need the interior ones, but we're going to need 1,000 by 1,000 by 1,000 drones. That's 1 billion drones. So we're going to have to move in order to get to a smaller scale, we're going to have to move to biomimicry. These drones, as they get smaller, the problem is the propellers don't spin as fast because their radial spin is the velocity, and you get into low Reynolds numbers where air becomes viscous. And insects deal with this really well because they can control the pitch of their wings in every possible way. So this was a spoof that was on the internet this week about the US government developing spy mosquitoes that could sample your blood and do DNA analysis and all that. I'm sure there's someone working on that, but we're not there at all. But again, here's the nefarious use of the good thing that I'm trying to make. Just looking at nature, it's mind-boggling that these insects can actually maintain energy because the storage volume is very, very small. So the cubic energy volume is very, very small. They're flying in syrup, basically. And they also are capable of swarming behaviors that are quite interesting. So we'd love to be able to create that big Hero 6 interface and do it by basically creating small mosquitoes or maybe hummingbirds, but we don't know how to do that. Now, why are we doing this? Because this is what we're made of. We're made of physical material, not pixels, not bits. And I think that this is how we learn. And I think Tim's work is very much in line with that. You know, if you look at how kids experience the world, it's very much through physical activity, experiencing how things interact. And it's kind of funny that you see the little babies now trying to swipe a magazine and they go like, Mom, it doesn't work, it's broken, battery's dead. This is how we communicate. We don't communicate over text and emoticons. Are we silly? We communicate by giving each other hugs, by being present, looking to each other's eyes. And all this is potentially lost when we go into the society of pure virtuality. And this is how we create. We love creating physical materials, and we have a 1,000-year history of creating, molding, and this is something that should not be taken away from us, because I think this is very much who we are. This is how we articulate. You cannot play the violin if you don't hold it in a particular way that allows you to communicate your muscle tension to the audience through audio. Hand waving doesn't do it, because physical is who we are. And with that, I'll take questions if we have time.